Hello everyone, welcome to RL106, which is Word Models for LLM Agents. Today we'll discuss reinforcement word model learning, basically teaching AI to understand the environment dynamics. We'll move from reinforcement learning from human feedback to understanding reality itself. Previously, we discussed RLHF, they teach LLMs human preference, and we demonstrate that LLMs can be aligned using many methods such as preference learning, reward models, and also PPO for alignment. But humans and animals still possess something many LLMs lack, which is what we call internal word models. Your dog may learn from reward signals after only a few experiences, but LLM agents still struggle to truly understand consequences, environment dynamics, and also causal changes after actions. In short, RLHF teaches what humans like, world models teach what reality does. Now, LLMs can talk, but can they predict consequences? We know that LLMs are already good at question answering, code generation, multi-step reasoning, as well as conversational fluency. But LLMs still struggle in many agentic environments that require many different things, such as anticipating action consequences, adapting to environment dynamics, understanding hidden causal structure, as well as long horizon interaction. And agentic intelligence must consist of more than language understanding. It also requires word understanding. And good agents do not just generate actions, they anticipate what happens next. Now, you may realize that your pet dog has a word model too. And biological intelligence has a superpower, imagining future consequences before acting. So basically, for example, your dog see the treat and you will predict that sit down equal to some sort of a reward. And human driving example, when we see yellow light, we may predict if I speed up now, it's probably dangerous. So it's not a good idea to speed up after I see the yellow light. And for chess example, the player may imagine if I move here, opponent may fork the queen. And in summary, humans and animals learn efficiently because they simulate outcomes, they can anticipate consequences, and also mentally model environments. And intelligence is not just reacting, it's actually predicting. So, what is a word model? It's actually very simple. For beginners, a word model is just predict what happens next. For engineers, we give it a term, just transition dynamics. And for researchers, we call it approximate the environment transition function. So basically, given the state and action, we predict what happens in the next state. And basically, it allows agent to see what the next state might look like before actually acting. And so suppose your robot plans to go to countertop, the robot may internally imagine there might be a knife there, and before even moving. So good agents do not only act, they internally simulate outcomes. And in this discussion, we assume for simplicity that all the state's actions are textual descriptions. And why does previous methods fail? Supervised fine-tuning requires many different things such as expert demonstrations and also exact target outputs, and the model basically learns repeating expert wording. However, memorizing exact word does not mean understanding the world. And so SFT teaches the agent to sound intelligent, but word models teach agents to think ahead. For example, human says there may be a knife on the countertop. SFT learns just to repeat the sentence, but word modeling should learn why the knife is likely there. You can think about this like a parrot can imitate words, but it does not mean it understands your kitchen. And SFT compresses demonstrations into parameters. RWML learns environment dynamics. And so let's now look at a brief detail in the method. Can we teach the agent to understand le monde or the world? And this is done through interaction, consequences, as well as reinforcement signals. And we want to understand how the world changes. And this is the core idea behind reinforcement world model learning, or RWML. And RWML does not just teach agents to imitate actions, it teaches agents to anticipate consequences. And so the idea is quite simple. We just ask the agent to predict the next state, reason about consequences, and learn from interaction feedback. So for example, if the robot says just want to go to a countertop, there might be reasoning that knives are often near countertops, and therefore the predicted next state might be you see a knife. And basically, given all the history, basically the previous states and the action for the time step t, and we want to predict the next state along with the reasoning tokens. So the big shift here is that we are going from what humans prefer to what reality does, and from preference modeling to consequence modeling. Now let's look at a RWML pipeline flow diagram, and you see that there's no expert label needed. The pipeline is very simple. We first roll out a trajectory, the agent observes something, they take actions, and we collect the rollouts and we put them into tuples. Basically, the tuples consist of all the prior states and the actions, and basically what is the next possible state. And this is the triplet. And after that, we subsample easy examples because these ones, they do not contribute much to the learning. And finally, we train a pi theta policy model to reason as the word model using GRPO. Basically, this is a modified version of PPO. We just use a very lightweight reward function, just compute embed-based cosine similarity, like is the simulated state very similar to the real state? If that's it, you just give the reward 1, otherwise reward 0. And basically, that's the whole pipeline. We roll out, we collect conditions, we predict next state, we compare with reality, and we do IR update. And so the environment now becomes the teacher. Instead of humans teaching the agent, the world itself becomes the supervisor. And so the step 1, we just let the agent explore, we collect interaction just like we do in RL stuff. We have states, actions, and for example, the kitchen, you may go to countertop, the next stage is see the knife, and the action may be open drawer, and the next stage is see the spoon. And we break them into transitions or trajectories, like each tuple consists of all the prior states and the actions and what happens in the next state. And basically, from the current history plus action, we predict the next state. And there's no experts, no labels, no stronger LLMs, and the environment itself generates the learning signal. And so the core idea is that the meaning is more important than exact words. And humans don't communicate using cosine similarity of tokens. Like if your friend says there's a spider behind you, you probably want to reply, sorry, wording mismatch. And so you just should compute the similarity between predicted states and real state. And RWML does not ask, did you produce the exact sentence? Instead, it asks, can you understand what happened? And we care more about understanding reality. Like for example, if the next day you see a knife on the countertop, the first prediction could be there's a knife near the counter. The second prediction could be the kitchen explodes. The first prediction should get a higher reward because it's more close semantically to the actual state. And so why do you use RL instead of supervised fine-tuning? Because supervised fine-tuning just repeat exactly what the teacher said. However, RL says figure out what actually works. For engineers, we are optimizing semantic correctness, consequences, and also behavior quality instead of just exact token matching. And for researchers, SFT can cause token level collapse, such as copy what the teacher said. And RL allows multiple valid reasoning paths with the same semantic outcome. And SFT, just like memorizing exam answers, RL actually understanding the material. And it teaches agent to optimize meaning, not just imitate wording. And now let's bring back PPO. And except we are doing what we call group relative PPO, basically. And traditional actor critic, there's actor network, there's critic network, we compute value estimation, Q functions. GRPO replaces critics with what we call comparisons. So actor critic is like teacher grades your homework. GRPO is you compare your answer with each other. And the philosophy here is that if we just simply sample multiple answers and compare them against each other. So let's suppose that the problem is what happens if the robot opens the drawer and the model samples find spoon, find knife, kitchen explodes. And let's say we chooses the option find knife. And we can compare the answer with the other two answers. And this is what we call the relative advantage within a group. So we take the reward, we subtract the mean, and then we divide it by the standard deviation. And the GRPO just says what prediction makes more sense. And everything looks fine for now until the agent thinks the exam is too easy. You probably should not train to do like 1 plus 1 equal to 2 for 10 million steps. And the idea is that many transitions are repetitive, trivial, and easy to predict. Like for example, go to kitchen, you probably arrive at kitchen, and your agent will not learn much. However, training on easy transition repeatedly will waste compute, teaches little new information, and weakens learning signal. An RWML solution is remove easy questions and focus on surprising difficult transitions. And the idea is intelligence grows faster when learning focuses on difficult situations. And now let's give brief examples from the paper. The paper gives two examples. The first example is the ARF world. This is just the kitchen. And imagine you are in the middle of the room and you see many different things like cabinets, stove burner, whatever. And the task is to put a knife in the side table. And before WMRL, the agent may like think that you should go to drawer one, but drawer one is closed, and he thinks that drawer one is now open but contains nothing. Drawer two also does not contain life, and max 30 step reached, and it fails to complete a task. And the paper shows that after WMRL, the task is like also the same task, and the agent now thinks that it is likely to be on the countertop one, and he actually be able to complete the task in 5 steps. Another example is the Tau2 bench. Basically, this is the customer agent, and you have multiple functions. And suppose the user asks the phone has no service for the past few hours, and the user has tried restarting already. And before training using WMRL, the agent may think that could you provide the phone number, customer ID, and the agent may be confused and reach the max number of steps. However, after training with WMRL, the agent will know that since the user mentioned they tried restarting, it's possible the airplane mode is on, and the user actually says they have turned on airplane mode, and so the agent will be able to correctly provide a solution and route the user to the human, basically, and they can successfully resolve the issue. And so the agent improved without being told the correct answer. So basically, they show that they can achieve the 19 points improvement in terms of reward and 7.9 points improvement for the Tauti bench after combining WMRL using with the real world rewards like the policy stuff. And they did this without expert demonstrations, no stronger teacher LLMs, and there's no task success reward signals. They only do it after they train using the word model, and there's no human annotations. So the word itself becomes the supervisor. And the agent just learns from interaction plus consequences. And nobody tells the agent, here's the correct answer. The agent basically learned by touching grass in the environment. And so why does fine-tuning makes models forget? We know that human intelligence is surprisingly stable. If you study chess for 10 months without talking about calculus, you probably won't forget about it after learning chess for 10 months. However, SFT can cause forgetting because it forces model to memorize exact token patterns, and large parameter updates may override previous knowledge, reasoning skills, or general capabilities. And after aggressive FFT, the model may forget things like math ability, coding ability, and reasoning quality, and this is what we call catastrophic forgetting. However, RWML teaches new skills without erasing old intelligence as much. They create gentler updates, less overwriting, and better knowledge preservation. And now, why are word models such a big deal? Because word models enable 4 aspects. The first one is planning. What should I do next? Anticipation, what happened next if I act this way? Efficient exploration, which actions are worth trying next? And low horizon reasoning, how will this affect the future? And without word models, the agent just doing speed running life blindly. However, with word models, the agent mentally simulates outcomes before even acting. And prediction is a core ingredient of intelligence. And where is AI heading next? Well, we went from chatbots to agents to world models to even autonomous systems. And future AI agents may need many things like memory, planning, simulation, environment understanding, and long term decision making. And the key insight here is that future AI systems should not just generate fluent language, they need to understand consequences in dynamic environments. And the future of AI is not just conversation, it's interaction with reality. And the final takeaways of this discussion is that RLHF teaches human preference, RWML teaches environment dynamics, and world models improve planning and decision making. And self-supervised RL can teach powerful agent behavior without experts. And the big philosophical shift is from predicting tokens to predicting consequences. And the final line, the future of AI is not just generating text, it is understanding reality. And now here's the reference for the paper that we talk about today, and you'll find the lecture versions on YouTube and also Bilibili. Thank you everyone for listening.